has two aspects basically. Scalability means either you want to accommodate a large database that cannot fit on one server, or even if it fits on one server, you want to basically accommodate or manage a large database. That's one aspect. That's one aspect. The other aspect is the ability to handle a large number of read and writes, which is usually as a result of having multiple concurrent users, multiple users. Your application becomes popular and many users are adopting it or coming to your website or whatever it might be. Then you might not have a problem with the data size, but you might have a problem with the volume of transactions and the volume of read and writes that your application is generating to your database. So scalability means by fact of just adding more resources, you can maintain the desired performance despite the presence of a large number of read and writes and or large database. Is clear? So scalability means I can handle either large database and or large number of concurrent users, which means a large number of reads and writes, by simply adding more resources. If your system can achieve this property, it is called a scalable system. Scalable system, it's not something magical like a system can handle a large number of users. That's not what scalability means. It means it can handle more users and more data by adding proportional level of resources. That's what scalability really means. So as this scalability expert from Amazon, a very well-known guy, Werner Vogels, a service is said to be scalable if when we increase the resources in a system, it results in an increased performance in a manner proportional to resources added. Okay? So a system that is not scalable is a system that no matter what extra resources you throw at it, you are not improving the performance. That is not a scalable system. Scalable system, if you're suffering from a lower performance or you're suffering from a large number of requests or suffering from a large data that you are manipulating and managing, you can basically solve the problem by adding extra resources. If your system can satisfy this property, then it is called a scalable system. Okay? So how scalability is achieved? There are two major approaches. Scale up, which is basically taking, in this context of a database, taking that server and adding more resources to it. More memory, more CPU, more bandwidth, network bandwidth, and more disk storage. Sorry? Yes, this is the vertical. Yes, this is the vertical scale, adding more resources to the same server.
So it will be single unit with big size.
With big size, yes. So you go for bigger server. But at a certain stage, as you know, you might hit the limit. Even if you have the money to buy the most sophisticated server, at a certain stage, it might not fit your needs. So you have to, at a certain stage, you will be forced to, if you can fit it on one server and you can afford buying a better and better servers every time you go to a next level of usage, then it could be fine. But in some cases, especially in the web scale applications that have had a large number of users and manage a large number of data or manage a large data, then most likely you need to scale out, which is also known as horizontal scaling. Okay, so in terms of database, there are two techniques that are used for scaling. There is sharding, and there is also called partitioning, and there is replication. Okay, so for sharding, you basically take your data and chop it into multiple parts, and each node will be responsible for one part. So this is an example here. I have three entities, A, B, and C, and a cluster of 3 nodes. Every node will take care of, let's say, one entity. Replication is having multiple copies of the same data, having multiple copies. So sharding, it does not address the problem of Yes, sorry, this one is address the problem when you have a large database. If you have a large database, then sharding will help you to accommodate a database that cannot fit on one server. You can basically shard it and partition it across multiple servers. And also your performance will be improved. For example, now you can route your reads to multiple servers, especially if you are not joining or you are not doing something cross shards, then your performance will be improved. But if you start doing things cross shard, query that spans multiple partitions, then your query performance will be suffering. So this one is mainly to address the big data problem. The replication, it does not address the big data because you are replicating the data in multiple nodes. But it addresses high availability. If one node fails or down, you can route your queries to other nodes. And also in terms of performance, its performance is improved. Performance is improved, but I will go into a little bit more details as we move forward. So we have sharding and replication. Yes, please. You want to say something? Okay. All right. Okay. So with sharding, you have one logical database. So as far as the applications are concerned, or users are concerned, they see it as one database, but physically it is partitioned in multiple databases. And there are many ways of doing it. One way is to use a range-based sharding. So for example, if I'm storing customers, I have a large volume of customers such as Amazon, so many customers, you might do a range. One node can take care of customers A to G, and second node H to P, and the remaining in the third node. And then you have some kind of router in the front, and it will route the queries to the appropriate partition based on the range that the query mentions in the where condition. So we can distinguish between horizontal sharding. Horizontal is that what I just explained. It's usually a range partitioning. So in this scenario, A's will go into one. The customers with last name A goes into one shard. Customers with last name C go into another shard. With last name M goes to M shard, and last name Z goes to Z shard. Usually it's not a one-to-one, usually it's a range. A to D and F to M and so on, okay? This is one way of doing it. The other way is the vertical sharding. So especially for the columns that might have a lot of data, you could partition them and put, let's say, the thumbnail as a column, you put it on a separate node, and the photos in another node. And this way, you have a much more scalable system. And you could combine, of course, both. You can combine horizontal and vertical sharding, and which is called the hybrid sharding. In terms of algorithms, now in a relational database, this is feasible, of course, but it's much harder. And usually only the big vendors like Oracle, Microsoft supports this. And usually in the enterprise license, you need to pay more for the license. And also in many scenarios, the application might need to be aware of the sharding. So that is the problem with the relational database. So it's not impossible, but it's hard to achieve in the relational world. In the non-SQL world, it is something out of the box. It is by design from day one. They put this partitioning and sharding in the design constraints and design goals. So it is there out of the box. For example, in MongoDB, it is there. Once you install it, you can do sharding. Now, in the context of something like MongoDB, since you have collections and collections have documents, and documents typically have some kind of key that uniquely identify them. Not only the underscore ID, you can have your own custom key that is unique, and you can index the documents based on that key. So in that scenario, all you can do, the sharding could be as simple as taking the key, applying some hash function, and taking that hash function and applying, let's say, modulus the number of servers. And you can know which node your document will go to. And if you recall, the document, you can design document to be self-contained. It has all the information. Let's say if you have a document that talks about or captures orders, you will have the whole order details in one document. So there is no need for joining or having multiple tables or whatever. You have one document that captures everything about the order. So it's very easy. The unit of sharding and partitioning is a document. All you need, take the key of the document, apply some hash function to it, and it will tell you which node you should go and either store or fetch the document. That's one way of doing it, using an algorithmic hashing. The other way of doing it is by using range hashing. But in this case, you need to have some kind of service, locator service, some kind of service that maintains this mapping between the range and the node. So whenever is somebody looking for a document with a range up to 10, with the key of the document is up to 10, they will have to look into node 0. From 10 to 30, they have to look at node 1, and so on. So you have some server that maintains this. And this server, this metadata is available whenever you want to do a query. It will help the router to make decisions where to send your query to. Okay. Now with sharding, there are a lot of challenges, especially when it comes to relational databases. With relational database, once you do sharding, there are a couple of problems here. First, sometimes you can get some imbalanced shards. For example, like in our region, we will have a lot of customers, especially if we shard based on the first name, a lot of customers starting with A. And this shard will be like a hotspot in your infrastructure or in your cluster. And also, your sharding will be imbalanced. For example, the Z will have very little number of records, and the A will have much higher number of records. So your cluster will be imbalanced. So, but this is for relational. For non-relational, they as I mentioned, they have most of them, or for example, the MongoDB, it has a component called the balancer that is watching the distribution of the documents through the nodes of the cluster, and it can, especially if you are using a range, it can adjust the range to make sure the nodes are balanced in terms of size of document that they are storing and in terms of number of requests they get. So it keeps that balancing automatically for you. So it's not infeasible in relational, but it's much more effort. Plus, you may lose some referential integrity and constraints, and you might need to put them in your application. So some of the constraints could be lost. What type of constraints I can think of? What type of constraints? I can't think of an example. Anybody can help me? Okay. Constraints that can be lost when we shard. For example, in here, simple constraints could be the email, for example, shouldn't be null, as an example, or last name. Those can be preserved, even if you do sharding, it can be preserved. Now, if you have some reference tables, for example, let's say you have cities table. Yeah, cities table is a reference table. You might have here you might have a column called city, and the city is referring to the city primary key in the city table. So you might lose that reference. You might lose that referential integrity, but you can easily solve that by duplicating the reference data in all the shards, in all the partitions. Are you following this example? So if you decide not to replicate that reference data like cities table, then you might have a problem. You will lose that integrity, and you have to enforce it in the application. You make sure that your users don't select cities that do not exist. Database will not help you if they try to insert a city in the city column for a city that does not exist in the cities table. But this also can be solved, as I mentioned, through. But you will be duplicating the city table in all the shards. And guess what? If it changes, you have to change it in all the shards to keep it synchronized. So you can see here there are issues once you move into sharding. And I mentioned also the rebalancing and resharding to make sure the data is kind of, to some extent, evenly distributed. It's not easy to decide which key to use for sharding. That's what makes it difficult. Okay, your transactions and your performance will suffer if you have queries and joins cross shards. Okay, so that's one solution for database scalability is sharding. The other solution is replication. And these solutions are not like one or the other. Usually in real life and in practice, they are used together. Yes, both together. So for replication, what you do, you are duplicating your data in multiple nodes. And for various reasons. One is to improve availability and make, if one node fails, the users can switch to the other node. And also you can improve the read and writes. Depending on the configuration, but you could improve the read and writes, particularly the read, depending on the architecture and the configuration you will choose for your replication. So one of the architectures is the master-slave replication. So the master-slave replication, what you have this is your application where the queries come from, and this is your master database, and these are the slaves. So master slave, what you do, the rule says all the writes must go through the master. All the writes must go to the master, and then the master pushes those updates and inserts and deletes to the slaves. Yeah. So if you do this, you basically these slaves, they could be a little bit out of date, so they might be eventually consistent. Of course, in here, there are many ways of configuring this. If you decide to make it synchronous, what I mean, when somebody makes a transaction, like let's say insert a new record in customer, and the customer is replicated in the master slave 1 and slave 2. One way to do it, you can put all in one transaction and say, I will only confirm that the insert is successful if the insert in the master, the slave 1 and slave 2 are done successfully. If all of them confirm to me that they received the new record and they have successfully inserted it into their customer table, then I will give you the good news that your transaction is successful. But of course, what this will create, your performance will suffer significantly because it has to wait for all these instances or all these nodes to confirm the commit. And don't forget, there is a network in between, and so it will take some time. So that's why in practice, the pushing of the update to the master is done asynchronously. What I mean by asynchronously, the master will say, okay, I received your transaction, I committed it, I give you the guarantee that I have done it, and that's it. Leave it with me, and I'll push it to the others. Yeah. So of course there will be some microseconds delay or some delays depending on your network, depending on the network conditions. So somebody might go to if they read from the master, they will get one result. If they read from the slave, they might get a different results. So once you introduce replication, you immediately introduce consistency. Another type of consistency. In here, what it means, consistency between the replicas. the replicas might not be consistent. And if you want to make them consistent, you might make the performance suffer. So it is a trade-off that you need to do. You need to decide how to configure this. But in most cases, especially in the relational database world, you have a master where all the writes come to the master, and then the master will typically just give the good news to the user, your transaction is committed, and it will asynchronously push the updates to the slaves. Okay. Now the reads can go to the slaves, of course, and this way you improve your reads, the read speed and the read performance, and the read you can handle more read requests, but your writes are still bottlenecked into one master. Yeah. Okay. Now, if you have some transactions where some reads that you really want to be consistent, you must push them, you must route them through the master. They must go to the master. This way, you will get the most perfect answer. But what's the downside? You're basically reducing your scalability, and you put in more load into the master. Yeah. So there are trade-offs between this in every architecture. Okay. And this can work very, very well in situations where you have many readers, but very few writers. Like the example of Wikipedia. We have so many readers, so they can go to any replica to read, and we have only few writers. So this will work very well. Okay. So I already explained if you do asynchronous updates from the master to the slave, you might end up with some eventual consistency. Consistency between the replica will be eventually achieved later at certain time. And if you really care about strong consistency for some queries, maybe not all queries you want very consistent results, you put them through the master. Okay, so this is the biggest problem. Once we talk about replication, you are talking about ensuring consistency and making sure that you might pay the price of having some outdated data when you read from some of the slaves. So this is one architecture, which is the master-slave architecture. The other architecture is the peer-to-peer architecture, where there is no master. You can read and write from any slave, from any node. There is no slave here, from any node, and they synchronize with each other. So this is, of course, much, much harder to manage, and you will get more problems with consistency. But in terms of your scale, it's very much scalable. You are scaling the writes and you are scaling the reads at the price of a lower consistency. Okay, that's what I want. That's the basic idea of sharding and replication. And keep in mind, for replication you have a master-slave architecture and you have peer-to-peer architecture. And in all cases, unless if you do synchronous pushing of update to the slaves, then you cannot really achieve 100% consistency. And if you do synchronous update to the slaves, then your performance will suffer, and this defeats the whole purpose of replication. While the peer-to-peer makes consistency even much, much harder to achieve. Okay. Now, some products out there already, even in relational, like the enterprise version of Oracle, Microsoft, they have these features. But it's not as easy to implement and as readily and cheaply available compared to non-relational database such as MongoDB. So let me show you now how the situation or how this looks like in MongoDB. So in MongoDB, sharding and replication is part of the engine. It's part of the architecture. If you take the architecture of MongoDB, out of the box, you get this sharding and you get this replication already built in. So in a real implementation, what you have is you might have in a real web, a large application, even the website, something like Al Jazeera or CNN or Amazon, when you have a website, it looks like there's only one address and one server behind it, but in reality, there is a cluster of servers answering your requests. And these clusters of servers are associated with the database. So in the relational world, most likely, in most cases, you might have a big, huge database. Although your application, in terms of web server and application server, it's scalable. There are many copies of the web server and application server, but your database could be bottleneck. That's easy in the relational world. In the MongoDB world, your database is also scalable to match the scalability of your application servers. So on the application server, you have what is known in the Mongo architecture. It's called the Mongos. This is basically the router. So your code that you're writing here, maybe your Java code, your Java implementation, or .NET or Node or whatever, or JavaScript, whatever language you are using, you will be using some driver, similar to what I just showed you before. You'll be using some driver, and that driver will connect to a Mongo server, and this Mongo server is really what it is a router. It is a router that will route the query to one of those nodes. So your data tier, your database, your physical database is basically is deployed in a cluster of machines. It's not only on one machine, it's in a cluster of machines, and each cluster in a cluster of machines, and each in a cluster of machines, each set of machines will take care of a particular shard. Your database is partitioned in multiple shards. So for example, here I have shard 1, shard 2, shard 3, shard 4. And then in each shard, I could have it replicated. I could have each shard, I might have a primary shard acting as the master, and I have secondary shards acting as the slaves. So the writes will go to the master, and then they get pushed to the slaves. So, and then the same thing here for shard 2, shard 3, and shard 4. So this we call replica set. Replica set. So for each shard, you have multiple instances. And you can configure this up to you. All this is configurable in MongoDB. You can configure how many shards you want, how many replica sets, how many replications you want. You can also configure that. And then you have the configuration servers. The configuration servers, they maintain, as we discussed in here, they maintain this, something like this. They maintain the range. So here is the range. This is the key of your document. Somebody is looking for, let's say, customer where customer ID is 2,500. We look up the table, and the key that you are looking for falls in this range. It routes you to the correct node, to correct shard. Yes. Now in the shard, if you are reading, you can read from any of replica. If any replica will answer your read request. For if you are writing, you have to go through the primary replica. That is basically in summary, this is the architecture on how it is done. So the whole engine is architected around sharding and replication built in from day one in the design of the database. Okay, so that's what I just explained. Let me just give a little bit of more examples. So this Mongo's components in MongoDB architecture, it's responsible for routing. And basically, as I mentioned, in terms of routing, it could be either based on simple hashing. It could be based either on simple hashing such as this. You just put the key, hash the key, get the hashed value, and then hash it based on the number of shards, and then you can land in the shard where that document will be stored. So this is a hashed-based.
This is not range. This is ring, right? It's another.
This one is basically
Based on the hash. Yes.
based on the hash.
Other than range.
Yes, this is different. Yes. So there are two ways, at least two ways, to do sharding in MongoDB. It supports either this hashing-based sharding or range-based. So either hashing-based or range-based.
It's called ring.
A ring in other databases, yes, they use those terminologies. In MongoDB, they just use hash-based or range-based. Okay, and basically the router will route you to the correct shard. And then once you land into the shard, you will find a replica set. Each shard has a replica set. As I explained, there is the primary replica, and there are the secondaries. So if you are coming to read, you can use any of these replicas. If you are coming to write, you go through the primary. By default, this is the out-of-the-box configuration. But you can, as I explained, you can change it. The configuration is changeable. So if the primary for some reason is offline, it goes down, an election takes place between the secondary replicas to elect a primary, because we always need a primary for it to handle the writes. Now you can configure it, as I said. You can, if any of these replicas, you can. There are some configuration properties that you can set. There is something called priority. If you set the priority to 0, that particular replica cannot be elected as primary. Okay, maybe that replica, I'm not sure the reason. Maybe that replica is hosted in a weak server. You want a replica to be only on these new servers that you just bought from HP or IBM. The old servers, they can be secondary but never be elected as primary. You can control this. Hidden is true, which means the replica is there and it's receiving updates regularly from the primary, but it's hidden. It cannot be accessed directly from clients. Maybe you have this replica just for reporting or for your internal use, for auditing or for some other use. In here, you have a slave delay. You can specify milliseconds of delay between the primary and the secondary. And this one will give you some buffer. If somebody does some silly things, you say, oh, hold on, I didn't mean to do that. I dropped the whole collection. Then you can quickly jump to this replica that is delayed, and you basically get your original data before you did the silly mistake. So you have some buffer there, of time buffer, to kind of recover if there are some unwanted changes that you made to the primary. So you can see here it's configurable out of the box. So this is what I just explained. Now even the behave of the replication, you can configure it the way you wish. So out of the box, it is this is the default behave. The default behave is all the writes go to the primary. The primary, once it accepts it in memory, once it does the change in memory, without even updating the secondaries, it gives you the good news, your transaction is done. Okay, so all the reads go to the primary, ensures strict consistency. Oh, okay, all reads goes to the primary. So in this case, what are we using the secondaries for? The secondaries are only for availability and fault tolerance. So this is out of the box. Out of the box, the primaries secondaries are just enjoying life, not doing anything. Only for bad days they will kind of come in and help. That's out of the box. But you can change it. Everything is configurable. You can configure it to say only confirm that transaction is successful after you put it in a log file in disk. So this is called journaling. This is the default in the relational database. Relational database cannot, because of durability, the D, because of durability, it will never tell you the transaction is committed until it records it explicitly in a log. But apparently in MongoDB, this is not the default, but you can configure it to do so. You can configure it to first write the change in the log, then confirm that the transaction is committed. If you wish, you could even push it another level and to say, you should only confirm that the transaction is committed after you receive confirmation from M number of replicas. This is an even much stronger consistency. Not all of them, but some of them. It's configurable. You can configure it to all if you wish. Okay, in terms of read modes, you have also different read modes. You can say only primary. I want to only read from primary. I want to only read for primary when it is less, when it's not too busy. Or I only want to read from secondary or secondary preferred or the nearest in terms of network topology. So you can see here it's very much configurable. All aspects of replication and sharding, it's configurable, and it is part and parcel of the actual engine. Now in sharding, you can have this range-based, hash-based, and round-robin partitioning. Okay. I think that's the last thing I want to say is, you remember this, keeping the shards balanced. So MongoDB has this splitter and balancer component. They take care of this automatically. So if there is a shard that gets overburdened, and the collection, the documents in that, the number of documents in that shard is too high, it gets migrated automatically by this balancer component to another shard. So this balancer is keeping track of the load of each of the shards, and it can balance this. Especially, of course, if you are using something like a range. If you are using something like a range sharding, no, you can balance it. You can change the range. You can change the range. For example, here, 50 to 90, I can make it 50 to 80, and then here, make it 80 to infinity. Okay, and then just change the documents and move them. That's what the balancer will do. So it will change the actual range and move the document to another shard completely to keep it balanced. Yeah, and of course all this is configurable.